Hi there. Today I'll guide you through the process of implementing custom amplitude tapering in your phased array design using the PathWave System Design, also known as SystemVue. Amplitude tapering is a powerful technique that allows you to suppress the side lobes by adjusting the signal magnitudes across different sections of your phased array antenna design. So if you have a design like this, where you have your signal and you have the splitter and you have the attenuator and the phase shifters, and of course some amplification going on, and if you have your antenna right there, you can apply custom amplitude tapering solely to the array attenuator. And there are different options, so there are different default algorithms that you can use to apply the amplitude tapering based on defined window functions. But today I'll be talking about the custom, where you'll be able to choose your own custom tapering and define which section of the array you want to apply the antenna amplitude tapering to. In order to apply the custom amplitude tapering to your antenna array, one of the very important things you need to do is to be able to know the exact location of the elements that you want to apply those custom amplitude tapering to. And the function or the feature that will allow you to be able to do that is what we call the phased array visualizer in SystemVue. What this allows you to do, you'll be able to visualize your phased array in a constellation, and you'll be able to see the allocated position of each of the elements, and this allows you to be able to know what the location matrix actually looks like. So in this example, we have a 4x4, very simple 4x4 array, and you can see the location matrix, so which is actually saying the first element is placed in location in the origin of that coordinate xy, and of course the numbering goes up like that in accordingly. So this actually allows you to see where you're actually applying your tapering. The next step will be to define a variable inside the phased array attenuator block called WinTap. In this case, you can name any use any variable name you want, and of course the window function is set to custom. What this allows us to do is to be able to set this variable in equation or in parameter, of course, and notice the normalization is set to yes. So this is to allow the maximum number of the value that we're setting here to be 1, and that means it's normalized. Before we continue in the process of applying custom tapering to our phased array, it's quite important to note that the custom window variable that we've just created is a voltage value. And that means we can calculate the attenuator based on this equation right there. And what that means is, for example, if we're applying a tapering of say 10 dB attenuation to a section of our phased array, so in that case the custom window value will be 0.316, and if you're applying a 5 dB attenuation, then it will be 0.5623. And in a case where we don't want to apply any attenuation, of course the value will be set to 1, and that's because we've actually normalized that variable in such a way that the maximum coefficient will be 1 where there is no attenuation applied. Now let's look at some examples on how to apply the custom tapering to different sections of our elements. So if you look at this picture right here, you see that I'm applying to the tapering to all the elements at the edges, and we're exempting elements 6, 7, 10 and 11 from the tapering that we're applying. And I've written this equation just to specify the matrix that of the element that I'm exempting, and of course I can set the value of attenuation that I'm applying to the other ones that I'm not exempting. And of course here I'm setting all the elements that I'm exempting the tapering to be applied to to be 1. And of course, this is actually the attenuator that I'm setting for the elements that I am applying the tapering to. So the results here, of course, when the attenuator is set to 0, that is no tapering applied. You can see the beam pattern right there. And when a 5 dB attenuation is applied to the element at the edges, you see the beam pattern. Of course, here we can see the value of the magnitude of the marker right there. So we lost a little bit of power there, but of course the side lobes are suppressed. And of course, this is the result for 10 dB. So when the attenuator is set to 10 dB, see the result, all the side lobes have been compressed, and of course we lost a bit of power at the center right there. Okay, so if you're working with a fairly large array, of course it might be a little bit tricky to list all the element numbers that you want to exempt. But in this case, you can use the column value to actually specify the numbers that are consecutive. Of course, in this case, for the red zone, of course, those are the elements we are exempting. You can actually set the number of elements with columns, so from 23 to 28 in this case, and that you still get the same setup as I explained earlier on. So in this case, for a 10 by 10 array, of course, you have the where no application attenuation is applied. You can see the beam pattern, and in this case we've applied a 10 dB to all the elements outside the red zone right there. And yeah, so you can see the side lobes have been suppressed, and of course we lost slightly about 1 dB of power at the bore site. And this is the case where we're applying to a 10 dB attenuation, of course, to the elements outside the blue zone in another case. And this is the exemption matrix right there, and of course we can see the side lobes as well, and it's roughly 1 dB loss at the power level as well at the center of the beam. So if you have even much bigger array, of course, where it takes a long time to be able to bring all the exemption values into equation by using column, there's still a way. Of course, you can actually use some equation, as I've specified here, to specify only the elements at the edges. So in this case, we just specifying the elements at the edges, in this case 34, 37, element 64 and 67. So of course within this triangle, with this rectangle, of course that's the element we want to exempt for that case. And for the red case, of course, we are exempting and specifying the values of the elements at the center, at the edges. So of course you can see similar result as we've seen earlier on. And lastly, even I took it a step further, you might want to apply different attenuator to different sections of your array. So in this case, all the elements in blue, we are not applying any amplitude tapering into that, and all the elements in the red zones right here, we're applying an attenuation of 5 dB, and of course the rest of the elements we're applying an attenuation of 10 dB at the same time. All of this tapering can be applied. So this might be the next step for you, maybe what you want to apply in your application. So in this case, you can use the same technique that we've done earlier on. So you specify the elements at the edges for the case where you don't want to apply tapering, and of course for your 5 dB tapering, which you can specify as well, you specify the elements at the edges, and of course the rest you can specify the attenuation you want to apply, in this case 10 dB. And all of these put together, you can see the overall beam pattern, which is way better than the previous one, and the the magnitude at the bore site is still very good. Okay, so that's it from us. So stay tuned.